Hey, I'm Zubin. I'm a consultant at WellTyped, and I'm going to be talking to you about this wonderful program called ghc-debug and a new backend I implemented for it. I suspect this doesn't mean a lot to many of you, so let's start with something I'm sure a lot of people have faced. Your Haskell program is eating all of your memory. What do you do? So, and over here, I have a graph of, yeah, I have a graph of GHC, which is a Haskell program using 100 gigabytes of live bytes. And this is terrible. So what do you do? Uh, Something you might do is you might stare at the code really hard, and or you might just insert bangs everywhere. Surely that will fix it. Or you can just hang your head in shame and rewrite it in Rust. But none of these things really work, so we want something better. Uh, So what's a better way to approach this? Well, GHC has a lot of profiling tools, and event log profiling is a very good option to diagnose and as a first step of diagnosing and understanding your problem. So GHC has a bunch of options. You can enable event logs by using plus /rth-l, and you can use different kinds of heap profiling modes, like -ht for profiling by type, or -hi for profiling by info table pointer. And over here, I have an example of the output you might get when you generate an event log and feed it through this tool called event log to HTML, which outputs pretty graphs, and you can look at what your program is allocating, when it is allocating, and so on. And you might use functions from debug.trace, like trace marker, which puts these vertical lines into your graph. So you can separate different stages of your program. And what this thing is a graph, it's a graph of GHC compiling Agda. And this is a bug me and Matthew fixed a few months ago. And each vertical line is a reload. So we see that initially GHC loads Agda into GHCI, and we end up with like a gigabyte of heap usage. And then we type :r in GHCI, and the heap usage increases, which is unexpected behavior. So it almost doubles to 1.7 gigabytes. And this is very unexpected behavior. You expect that when you reload a project, you don't use more memory than you did before. So this was a bug in GHC that we fixed, and this is how we started diagnosing it. So we reproduced the test case, and we generated an event log using info table profiling in this case. So this is quite useful as a starting point. It tells you what you're allocating, when you're allocating it, and if you look, if you open event log, if you use on the HTML file it generates, there's a detailed tab where it tells you exactly what was allocated and where it was allocated. So you might see a list of constructors that make up the heap in your program, and this is with info table profiling, so you have the constructor name, you have what kind of thing it is, so these are all constructors, and you have their types, and you also have their locations, so the exact source location where this particular constructor was allocated. And this is quite useful, but unfortunately, it's just not enough sometimes, because you can see, okay, we were allocating lots of these cons cells. This is cons this is just the list cons constructor, and we are allocating a lot of these from somewhere in the base library. This is not really helpful to you, right? As if you're my program is allocating a lot of cons cells in the base library. So where do you go from here? So this gives you an overview of what kinds of things you're allocating and what are things you might want to look out for. But you really want more than this, much more. You want to understand why these things, so allocations themselves are not a problem, at least for what we are doing, which is memory profiling. It's why are these things being retained, which is really the issue here. We could be allocating things, but if they're just garbage anyway, maybe that slows our program down, but that's not what you're looking at right now. We want to figure out why are these things in the heap and why are they staying in the heap. So enter ghc-debug. Right. So ghc-debug is a program that lets you do precise heap analysis, and you can search and filter through all the objects in your heap using a friendly TUI interface. And there's a more advanced interface if you use ghc-debug as a Haskell library. And if you can think it, ghc-debug can probably do it. You can do any kinds of analysis on what kinds of objects are on your heap. So you might, for example, look at all byte strings over 1 MB of size in your heap, or you might look at certain constructors, and you can do basically any kind of query you might want to answer about what your Haskell heap looks like dynamically at runtime. You can do it using ghc heap. So what does this actually look like? So this is on the same ghc program compiling Agda. This is the ghc-debug break terminal user interface, and it looks a bit complicated, but what we have here is, so if you go back here, we see that we were allocating a lot of these GRE things, which are these things that the ghc renamer uses, and it's basically something that's generated by the front end. And we want to understand why are these still in our heap, and why do we have so many of these. So we've searched for this constructor, and ghc-debug sampled our heap, and it's given us a few occurrences of this constructor, these GRE objects, and you can scroll to any one of these objects, and you can expand them. When you expand them, you get a bunch more information. So the first 4 or 5 objects are not expanded, but this final one is. And what you see is the first entry is a cost center stack associated with that object, so you can figure out exactly where it was allocated. So in this case, you can see it was allocated in this module ghc.name.reader, and in this function force global RDR env3. And you can expand the cost center stack to actually get a whole stack of locations. And for this, you need profiling, but that's quite useful to figure out where these things are allocated and how exactly your control flow got to that point. This tells you everything about that. You have, this thing has 5 fields, and you can see all the fields there, which is not very interesting. We don't really care about what's inside this constructor. We care about why is it still on our heap. So underneath that, these numbers, this list of things show you a retainer stack, which is essentially a path from that object to a GC root. So at the bottom of the stack, you can see you have these TSO objects, which are thread state objects, which are the fundamental GC roots in any Haskell program. And each thread state, they basically, each Haskell thread has a corresponding thread state object, and that's a GC root. And each thread state object has a stack, which is where your code's being executed, and your stack is pointing into the heap. And so in this case, we see the stack is pointing into a list, which is pointing into various things, which is pointing into some thunks, and finally, you have a bunch of map cells, and finally that points into your GRE object. So you have this whole stack that explains why this particular object is still memory. And those colors here, what do they mean? Well, this is not what this talk is about, but earlier we implemented errors profiling for ghc, which lets you mark different objects that are allocated at different times in your heap. So in this case, these things, I'm sorry, I'm colorblind, but this is green, I think, here, and that's orange. So the green ones are objects allocated earlier in an earlier era, and these orange ones are objects allocated in a later era. So at this transition between orange objects and green objects, we see there's something suspicious here, where new objects are holding on to old objects, which was exactly the problem we had in this graph here, where our new compile was not releasing things allocated in the first section of this graph. So this, it can allow us to pinpoint exactly where things are going wrong. And you see we have a couple of thunks here. This is not just a simple thunk leak, it's a bit more complicated than that. But in many cases, if you have a thunk leak and you want to know exactly where can I put a single bank pattern and then avoid retaining all these things, ghc-debug tells you exactly where to do that, and it'll give you a source location of what you're doing. So this is ghc-debug, and if there's one thing I want you to take away is that ghc-debug is a wonderful program, and if you do any kind of production Haskell work or even educational work, it's a great tool for looking into your heap. But that's not what this talk is about, and these are some things how you can search your heap using ghc-debug. You can add filters for various things and pinpoint exactly what you're looking for. So how do you use it? You have to instrument your program. You import this module from this package ghc-debug stub, and you wrap your main in this with ghc-debug thing. And how does this thing work? You have a debuggee and you have a debugger. The debuggee is the Haskell process whose heap you want to analyze, and a debugger is a Haskell program written using the ghc-debug library. And sorry, the ghc-debug common is mostly Haskell. That's a typo there. But ghc-debug stub is the thing you link into your debuggee, and these two things communicate via Unix socket. So the debugger asks the debuggee about various things about its memory, and the debuggee answers those questions over the socket. And this is great, and now you might think, okay, we can continue programming in a lazy functional language with a garbage collector, so everything's fine with the world now. But that's not quite it. So sometimes you might want to analyze your application might go wrong in a production environment, and maybe you want to understand what it is doing in that production environment. So we'll take a closer look. So so what does this thing do? It calls this foreign function, and this is in some C++ code, and it starts a server over some socket, and finally it runs your main function with some cleanup. So looking closer at what this foreign function does, it starts a server and starts accepting connections on that socket, and once it accepts a connection, it reads an integer from the socket, and this integer corresponds to a command. And in this case, one command is command get closure, which tells you, which asks the debuggee, okay, give me the raw bytes that make up this closure. And what we're doing here is we're reading int64 from the socket, and we're casting it to a stg closure pointer. So we're casting an int we read from over a serialization interface into a pointer, and we're computing the size of that closure. We're assuming it's a valid pointer to a Haskell heap object, and we're responding to the client with basically the contents of that memory at that location. And this just breaks all your process isolation, and this is really code you should not be running in a production system because it just breaks all your security boundaries. So what do we do instead? There's a standard way to peek into the memory of Haskell of any program, and that's called GDB. And you can connect to processes via GDB, and it requires some capabilities and such. You can just use sudo, but it doesn't break your process isolation boundaries. And what can we do if we just connect to a program with GDB? What can we do? Can we interpret its heap data structures? Well, we can if we have debug symbols, and these allow us to locate various RTS data structures and decode them. And GDB comes with a serviceable Python API. It's very stringly typed. It's not the best, but it works. So instead of doing this, linking in the socket stuff into our debugging process, we just connect to it via GDB, inspect its memory, and serve that over the socket in the format that ghc-debug expects. So you can use all your existing ghc-debug libraries and tools. So what does this actually look like? So in the stub, we had this thing where if the debugger asked us to list the roots of the GC roots of our Haskell program, we would call into the RTS and collect all the roots of our Haskell program. And on the left-hand side, you have an RTS function which lists all the threads, which are those TSO objects we saw earlier in your Haskell program. And what it's doing is it has a bunch of, it's looking into the RTS data structure. So each generation has a bunch of threads. Each set of threads is stored in a linked list. So what we do is we translate that into Python, and basically the same code. It's the same code, but written using the GDB API. So, and it's almost nicer in some sense because we have actual coroutines in the form of generators instead of what we're doing over there with a callback. But we just translate this code into Python, and we end up with this, these kinds of functions. And what we end up with is 700 lines of Python, which is versus 1,000 lines of stub.cpp. And you can maintain process isolation boundaries. You can snapshot your memory using gcore. Just take a core dump of your process, and then you can analyze it later. And ghc-debug has support for snapshots, but these snapshots were very slow because they basically trace through your program, starting at the GC roots. Whereas a core dump is just walking over your process memory, dumping it to a disk along with the memory mappings. So this is really fast. It takes a few seconds versus minutes. And you don't need to plan ahead to debug production Haskell services. You can just take a core dump, inspect the memory. And there's some stuff about knowing when to pause, but I'll put the slides up and you can read this later. And yeah, and how do you use this? I have links. You need debug symbols for the RTS, but these are quite easy to get. And future versions of GHC will ship with debug symbols for all variants of the RTS. Currently, you need the debug RTS. And yeah, links. And thanks to Mercury for sponsoring this work. Thanks to Hannes for cleaning up the code and writing documentation. And Matt Pickering and Ian Kim for all the support. Thank you.
All right, thank you. So we have some time for some questions.
Hey, yeah, so this is great if you want to add a strict, right, because you're keeping too much stuff around. But what if I have the opposite problem, right? Sometimes I'm not lazy enough, so I kind of put a bunch of stuff in memory, and then I have to wait a while until I actually consume it. So could this generate like a time graph, like, you created this value, but you didn't use it for 5 milliseconds, and then, so the opposite way, kind of.
You can do that using error profiling, which you can have an error, which you can bump in Haskell code, or it can bump on EGC, and you can see. There's also retainer profiling, which does a lot of the same thing. But ghc-debug basically looks at a single snapshot of your process's memory. So you need additional information if you want to track things across time.
Okay, thank you.
But there are ways of doing that.